So we just learned about first derivatives, or what we've been calling derivatives. They're also called first derivatives once we start to talk about higher order, which means a second derivative or a third derivative. Okay, so here's your definition. See if this makes sense. This is saying that the second derivative, right, this is the notation for first derivative. So you got two little apostrophes here. The second derivative is the derivative of the first derivative. Okay, so we get like two different notations here that's convenient for us. This is a notation for a derivative, and so is this. And this means the derivative of the first derivative. Okay, and then you could have a third derivative. I think you might see it like that. And then when it gets higher than that, then they'll put a little number up here, which we won't really get into. I think second derivative is pretty much as far as we'll go for the most part, unless we're just practicing. And there are some good applications of second derivative, which we're going to learn. Okay, so let's take a couple examples and see if you can find the second derivative of this function. So let's say 4x cubed minus 6x squared minus 18x minus 1. So give that a try. Okay, let's take a look using our new rules. We got four rules we can use here: the sum and difference differentiation rule, the constant multiple differentiation rule, the constant differentiation rule, and the power differentiation rule. So see if we're comfortable with kind of bringing them all together. Now I'm going to bring the 3 down. I know I have to multiply by 4, so maybe I can go right to 12. Take 1 away. Bring the 2 down, multiply by 6. That's 12x to the first. 18x, slope of the line is 18, negative rather, and then the slope of 1 is 0. Second derivative, same thing, the derivative of the first derivative. You don't really need to do this step, but just to point it out, it's the derivative of the first derivative, which is 24x minus 12. All right, how about an application? You've probably seen these functions before. They're how an object falls on Earth based on our gravity, constant acceleration due to gravity, in a vacuum. So you've probably seen this. This is meters. This would be if it's 50 meters from the ground. Initial velocity. Let me try that again. We call this, the position function typically is called s. So this would be s naught, its initial position, 50 feet above ground. Initial velocity, v naught, positive, so it's thrown up. So you're on a 50-foot building and you throw it up in the air. And then this is a constant acceleration due to gravity on Earth. It's not 4.9. You might remember 9.8 meters per second squared. We're going to see how this constant relates to that. Now, if we did this in feet, you'll see both of these a lot this semester. This is a real typical useful application for Calc 1. If it's in feet, we have the initial velocity is roughly 20 meters per second is roughly 66 feet per second. And 50 meters is roughly 164 feet, roughly. And this is the model an object will fall at if you throw it off a 164-foot building, throw it up in the air at 66 feet per second. Its position will be determined by this function if it's in a vacuum. Doesn't matter what the mass of the object is. Okay, so let's interpret. We kind of already know what the first derivative is. We talked about this when we established the derivative. The rate at which the position changed would be, just think about the units, it would be meters per second, right? That's the instantaneous velocity. That's the derivative. Real important, the derivative of the position function is the velocity function. And I would get negative 9.8 t plus 20. And then how would you describe how velocity changes? What do you call that? Acceleration, right? So the second derivative of the position function is the acceleration function. And this should not be a surprise. It's constant. Do the math, right? That goes away. Constant. This is a linear function now, your velocity. So this is just 9.8 constant on Earth, which makes sense, right? Something accelerates on Earth in a vacuum at a constant rate. Meters per second squared. And then anything here, if I asked you what's the velocity after 1 second, would be in meters per second. What's the acceleration after whatever time, meters per second squared? Constant, that would be an easy one. Okay, so this is a question I like to ask. I can ask you something about the position of the object, the velocity of the object, the acceleration. How about this? Here's a question we're going to see a lot. When does the object reach a max? Okay, so we have to do some interpretation. What's the velocity? If we're picturing what's happening here, here's your building, 50 meters high, and it's because the velocity is positive, it goes up in the air. Of course, gravity at some point will bring it down, and you have something like this, and it is modeled by a parabola. Domain would be 0 to whatever the time is it hits the ground, which we could find. We know how to do that. That's an algebra problem. So I want to know what the time is right here. So we have to do a little thinking and a little interpretation. It's going to be at a max when velocity is what? Velocity is positive, positive, positive. And then it's negative, right? If you're in the down direction, it's negative velocity. So what's the velocity here? 0. And that's a big topic for us. It's a maximum, it's velocity 0, it's a horizontal tangent. They're all the same thing. So how do I answer that question? Well, I just take my derivative function, which we're going to do a lot in here, a couple different interpretations, and set it to 0. And for this function, it's going to be pretty easy to solve because the velocity function for these types of problems is a linear function. So I'd add 9.8t to both sides. And I divide by 9.8, and I get my answer. The object reaches a max when t equals 20 divided by 9.8, which is about 2.04 seconds. Okay, so an application of our first and second derivative.